Before I do some examples, I just want to review what polar coordinates are and how to use them in integration problems. If you're already comfortable with this, you can skip ahead to the examples. So polar coordinates are just another way to describe the position of a point in two-dimensional space. What we're used to is Cartesian coordinates. If I draw a point in space, I can tell you how to get to that point by giving you two numbers, the x-coordinate and the y-coordinate. A polar coordinate system is just an alternative way to describe how to get to this point. Instead of telling you the x-coordinate and the y-coordinate, I'm going to tell you how far away from you are from the origin, and then I'm going to tell you the angle that you make with the positive x-axis. Distance from the origin, we call that r, and the angle made with the positive x-axis is theta. Using these two numbers, we can describe the position of any point in space. That's it. That's what polar coordinates are. In terms of multivariable integral calculus, there's two main things to know about polar coordinates. One of them is how they're related algebraically to Cartesian coordinates. But this is just trigonometry. This is nothing new. The thing to observe here is that this is a right triangle. So we can relate r, theta, and x and y using trigonometry. For example, by the Pythagorean theorem, x squared plus y squared equals r squared. If we know r and theta, we can get x using the cosine function. Cosine of theta is x over r, so that tells us that x is r cosine theta. Likewise, using the sine function, we can relate r, theta, and y. In particular, y is r sine theta. I'd say these are the main equations to know in terms of converting between polar and Cartesian coordinates. The other main thing to know about polar coordinates is that when you take an integral in Cartesian coordinates and convert to an integral in polar coordinates, we have to know how things change. In particular, suppose I start with a double integral or an iterated integral in x and y, and I want to take this and turn it into a polar coordinate integral. Well, we can figure out how to describe the corresponding region in terms of r and theta. Likewise, using these two equations up here, we can take x and y and convert them in terms of r and theta. So the function we're integrating would turn into f of r cosine theta, r sine theta. The tricky part is how the differentials change. I'll just skim over this very briefly, but dA, a small change in area in the xy region, looks like this. A small change in area in the r theta world in the xy world corresponds to a sector kind of like this, bounded by two angles and by two radii. In other words, small chunks of area don't correspond exactly to small chunks of area in the two worlds. So because of that, we need a fudge factor. That fudge factor is an extra copy of r. So in practice, the main takeaway from taking an integral in x and y and converting it into an integral in terms of r and theta is that the differentials change from dx dy to r dr d theta. We'll talk about this in more generality when we get to change of variables, but for polar coordinates, this is how it works. This is an example of using polar coordinates to evaluate a double integral. The region we're integrating over is a disk contained in some circle. Looks like it's a circle centered at the point 0, 1 with radius 1. And the function that we want to integrate is 1 over the square root of x squared plus y squared. A couple of remarks here. First of all, I claimed that polar coordinates are going to be helpful here, and I'll give you two superficial reasons why I might suspect that before I even do the problem. One of them is the fact that the region we're integrating over is a circle. In general, polar coordinates describe circles quite naturally. Now, this circle we care about isn't a circle centered at the origin, so we will have to be a little careful, but the fact that we're dealing with some kind of circular disk region, that's one indication that polar coordinates might be useful. The other indication is the fact that one of the things in the function that we have to integrate looks like x squared plus y squared. Very often, if you see x squared plus y squared anywhere in any form, that's an indication that polar coordinates will behave nicely with respect to this problem. Now, like I said, I wouldn't take this as a rule. These are just indications that this is a good idea. Also, we may not have to use polar coordinates. You're welcome to try other things if you want, but it might make the problem easier. Okay, so as usual, the first thing I'm going to do in this problem is sketch a picture of the domain that we're integrating over to get a feel for how to describe the region appropriately. The region E is defined by this circle equation. Like I mentioned, this is a circle with center 0, 1, with radius 1. That means it's going to look something like this. Ultimately, what we're going to do is we're going to use polar coordinates to convert this Cartesian double integral into an iterated integral in the r theta world. So let me start this off. We've got this double integral over this disk E of 1 over the square root of x squared plus y squared dA. Our end goal is to write this as an iterated integral with respect to r and theta. The function that we would integrate in this case would be 1 over, well, x squared plus y squared is r squared, so the square root of x squared plus y squared is r. Now dA, which we can think about as corresponding roughly to dx dy, when we convert to polar coordinates, we pick up this extra factor of r. So the dA is going to turn into r dr d theta. And that's really convenient. The r's cancel out, so the actual integration will be easy. We just have to figure out what the appropriate bounds are. So I put theta on the outside, which means the way I'm thinking about doing this integration is fixing a value of theta. So I fix an angle, and then I let r range from something to something. I fix a value of theta, and I let r vary, etc. Our slices look like this. Let's think about the bounds for r first. Geometrically, it looks like we're always starting at 0. In other words, the rays, these blue rays that I'm integrating over, they all begin at the origin. So for that, we might suspect that the lower bound for r is 0, and that would be correct. What's trickier is the upper bound. The upper bound for r is not constant, right? Because if I walk along this ray, the length of this blue ray is definitely shorter than the length of this blue ray. At peak, when I walk in this direction, the farthest I walk out is 2, because that's the diameter of this circle, but the upper bound for r is not going to uniformly be 2. Writing a 2 here would be incorrect. An upper bound of 2 would mean that no matter what angle I walk in, I walk a distance of 2. And that definitely doesn't happen. That would get us a semicircle centered at the origin of radius 2. Not my greatest semicircle, but that's okay. So the point here is that r depends on theta. And we need to figure out precisely how that happens. How do we do that? Well, the upper bound for r is determined by this red circle. This boundary circle here will tell us how r depends on theta. We have to work with this a little bit. So I'll consider the boundary equation x squared plus y minus 1 squared equals 1, and my goal is to convert this into polar coordinates and cross my fingers and hope that it tells me what an upper bound for r is. Now we could plug in x and y and go from there from here, but I think this might simplify a little bit more if I expand this quantity here. This is the same thing as x squared plus y squared minus 2y plus 1 equals 1. Then I can see the 1's cancel out. So this Cartesian equation is equivalent to x squared plus y squared minus 2y equals 0. Okay, and if we convert this to polar coordinates, well, I've got an x squared plus y squared here. That's r squared. Minus 2 times y. Y is r sine of theta. And then I could divide by r, assuming that it's non-zero. R is non-zero everywhere except the origin, so in practice this is okay. This turns into r equals 2 sine theta. There we go. This is exactly how r depends on theta. In particular, the upper bound is 2 sine theta. Now we just need the bounds for theta. There's a couple ways to think about this, but the shape E lives entirely in the upper half plane. Because there's nothing living in the lower half plane, the angles that we care about look like this. In other words, to sweep out this entire red disk, it suffices to consider angles starting at 0 all the way to pi. And indeed, those are the bounds. This kind of thing is a little weird the first time you see it, so you might have to pause the video and think about this for a second. But you can convince yourself that those are the relevant bounds for theta. And there we go. We've now successfully turned this double integral into an iterated integral in terms of r and theta. So continuing from up here, this will be the integral from 0 to pi, integral from 0 to 2 sine theta. R over r cancels out, so this leaves us with a dr d theta. And then this is a pretty easy integral to do. 0 to pi, antiderivative with respect to r here is going to be r. I evaluated my bounds, 2 sine theta and 0. Plug in 0, you get 0, so we're left with just 2 sine theta d theta. And then we take it home. Plugging in pi and 0 and subtracting, it looks like will get us 2 plus 2, which is 4. Success. In this next example, we're given an iterated integral in terms of x and y. Now, the point of this video is polar coordinates, so that's what we're going to use. As always, you're welcome to try it without polar coordinates. You can turn off the video, say, Joe, I do what I want, and try to evaluate this in Cartesian coordinates. I do think polar coordinates will be useful, though. To reiterate the comment I made in the previous example, there are 2 reasons why I think that might be the case. One of them is the fact that in the integrand I see x squared plus y squared. That tells me that when I convert this to polar coordinates, the function will turn out pretty nice. The other reason is this upper bound here, square root of 4 minus y squared, which is an x bound. And I have enough experience with circle equations to recognize that this is going to cut out part of a semicircle. So in some sense, I have a bit of a circular region that I'm integrating over. So just like in the previous example, I have a couple indications here that polar coordinates will be helpful. Now in a problem like this where we're given an iterated integral in Cartesian coordinates with Cartesian bounds, the most difficult part is going to be figuring out exactly how to describe the region in the r theta world. So I'll start off as I almost always do, and I'll try to draw a picture of the region, and in particular I'll be explicit about the bounding data. The inner bounds tell me that x ranges from root 2 to square root of 4 minus y squared, and the outer bounds tell me that y ranges from 0 to root 2. To get a picture of this region, I'll do what I usually do, and I'll take this inequality here and generate the boundary conditions. This top inequality, when I turn it to an equality, turns into x equals the square root of 4 minus y squared. And this lower inequality turns into x equals the square root of 2. Likewise, we have the boundary conditions y equals 0 and y equals root 2. Now, if I rewrite this equation a little bit, like I said earlier, I recognize that this is part of a circle equation. I would get x squared plus y squared equals 4. That equation is going to turn into a circle like this. The other equation that we have here is x equals root 2. Because this circle I drew has radius 2, I may have said a second ago 4, I meant to say 2. X equals root 2, which is like 1 point something, is going to be a vertical line probably sitting here-ish. Now if I do the same thing with the y values, I'm going to get y equals 0 as one of the boundary conditions. Well, that's the x-axis. I get a line like that, and then I get y equals root 2. And I can already kind of see that probably the region that we care about is this little sliver right here. So I'm assuming that y equals root 2 is going to be given by this line right here. And so the region we care about is right there. Great, we have a lovely picture, but we have to figure out how to describe this in polar coordinates. Typically, anytime you set up an iterated integral in polar coordinates, not always, but usually you're going to think about r as being the inside integral. So let's think about that first. We want to think about fixing an angle theta, which in my picture maybe looks like this, and determining the appropriate bounds for r. Fix an angle theta and look at this ray. Fix an angle theta, look at the ray, etc. This region's a little weird for a couple reasons. The first of which is r doesn't start at 0. In the previous example we looked at, every ray that I drew started at the origin. That's definitely not the case here. And the first time you look at something like this, it might be a little intimidating to try to figure out exactly how r depends on theta. The takeaway from this example and many of these examples is that while geometric intuition is great, and while drawing a picture is important, you want to trust the equations. Trust these equations. What I'm going to do is I'm going to take this data, turn it into polar coordinates, and the bounds for r will just algebraically fall into my lap. And I don't really have to even worry about getting information of the bounds from the picture. So let me write what I mean by that. The upper bound for r is given by this equation x squared plus y squared equals 4, which, convert this to polar coordinates, this turns into r squared equals 4, and so r equals 2. That's going to be our upper bound for r. And hopefully that makes sense geometrically. The upper bound for each of these rays is given by this circle, which is a circle of radius 2. So from a geometric perspective, it makes sense that the upper bound is 2. What about the lower bound? Well, what equation determines the lower bound for each of these rays? It's this vertical orange line here, right? That was the line x equals root 2. This is what's going to tell me the lower bound for r algebraically. Take x equals square root of 2, convert it into polar coordinates. Well, x is r cosine theta. So I get this equation, which looks a little weird, but just solve for r. And r is root 2 over cosine theta. That's the lower bound in this integral. So ultimately, once we set up the iterated integral, we have the r bounds. Again, getting something like this from the geometry of the picture, I think would be pretty hard. And a good way to approach finding bounds in terms of polar coordinates is, again, trust the equations. Now we have to think about the bounds for theta, and then we'll set the integral up and go from there. It looks like the lower bound is given by the x-axis, which is an angle of theta equals 0. The slightly trickier one is the upper bound. It looks like we sweep out angles all the way up to here. That's the upper bound that we care about. There are a number of ways you could think about this. For example, you could pretty much eyeball it and you could say, well, that blue line that I just drew passes through the point root 2, based on the intersection of these two lines. So you could say, okay, I know that angle is going to be pi over 4. To approach this a little more methodically, though, we could recognize that this upper bound is given by the intersection of these two curves. It's given by the intersection of x equals root 2 and y equals root 2. And we know that in general, tangent of theta, when we talk about how polar coordinates and Cartesian coordinates are related, is y over x. So at the relevant point we care about, when y and x are both root 2, we get tangent theta equals 1. And therefore, using some contextual information with the picture, we know that theta has to be pi over 4. So there's our upper bound for the theta integral once we set this up. And there we go, we've done the hard work. We've figured out how to describe the region. Now we just have to take the original Cartesian integral up here, convert it into polar. So here's the original iterated integral we began with. we're going to convert this into an r theta iterated integral. dx dy, as usual, we pick up an extra r, so this turns into r dr d theta. The outside bounds, in terms of theta, we decided that the lower bound is theta equals 0, and the upper bound is pi over 4. And the r bounds, or in purple up here, the lower bound is root 2 over cosine theta, and the upper bound is 2. The last thing we have to do is just convert this integrand right here. The numerator is y, which is r sine theta, and the denominator is x squared plus y squared, which is r squared. Then after some simplification, all of the r's cancel out. We have r squared over r squared. So we're left with sine of theta dr d theta. At this point, this is just a regular iterated integral to evaluate. So continuing on, the antiderivative with respect to r, in this case, is going to be r sine of theta, since sine of theta is constant. And I'll evaluate that expression at my upper and lower bounds in terms of r. Plugging in those bounds will give us 2 sine theta minus root 2 sine of theta over cosine theta is tangent theta. Then we have a theta integral to do. Integrating sine of theta is easy. So it'll give us a negative 2 cosine theta. And then tangent theta, since tangent theta is sine over cosine, a simple substitution there will show you that the antiderivative of tangent is negative log of cosine with an absolute value. So with that negative sign, I can turn this into a plus root 2 log absolute cosine of theta. You can think about that for a second if that was a little fast. Plug in pi over 4 and 0, and we are done. So we'll see if I can do this in my head correctly. When you plug in pi over 4, cosine of theta is root 2 over 2. So this will turn into negative root 2. Likewise, cosine of theta is root 2 over 2 again. So this will be plus root 2 log of root 2 over 2. Minus, plug in 0 for theta. Cosine of 0 is 1. So minus 2 is going to turn into a plus 2. And then since cosine of 0 is 1, I get a log of 1, and I have no contribution from that term. And in the small chance that I did that last step correctly in my head, that'll be the final answer. Done.